Good day, everyone. Thanks for attending this webinar. Welcome. This will be a webinar on the optimization of steam turbine maintenance and scheduling using predictive maintenance workflow. I'm one of your hosts or presenters today. I'm Peter Randall, a rotating equipment engineer here at Sasol, and I'll be co-presenting with Boitumelo Manchi from Optimum Solutions.
Good morning. My name is Boitumelo Manchi, and it is a pleasure to be here. I'm an electrical and biomedical engineer, and I work as a solutions engineer at Optimum Solutions. As part of my role, I get to work quite closely with a lot of customers within the mining and manufacturing space, helping or supporting them in solving their various problems, or even introducing smart technologies into their operations. And this presentation will display an instance of just that. Thanks, Peter.
Thanks, Boitumelo. So moving on to the agenda. So we'll cover a bit of a background, some content on fouling and how that's important to us, fundamentals of steam turbine operation, and then we'll run you through the predictive maintenance workflow, looking at the pre-processing, the analysis, model development, and then the deployment. And we'll conclude with some comments. So just to start off with, just a little bit about Sasol. So Sasol is a global chemicals and energy company. We have operations in 30 countries, and we are also one of the largest producers of synthetic fuels in the world. And we also have the world's broadest integrated alcohols and surfactants portfolio. I'm one of the rotating equipment engineers located at our Secunda facility, which is quite a large facility covering a geographical area of more or less about 20 square kilometers. So now I'm going to go forward into the equipment that we're dealing with today's project. It comprised of a series of 7 compressor turbine trains, each one with a megawatt rating of about 13.5 megawatts. It's a condensing steam turbine running at about 7,000 RPM with speed control there. So, and then additionally, we also have a pressure controller which will control our wheel chamber pressure when it measures at 2550 kPa. So that'll basically cut back steam flow to limit that pressure at that value. So then the problem statement is actually that these particular steam turbines suffer from fouling, and that fouling occurs in a period of normally between about 8 months and to a year. And we want essentially a bit more planning and predictability, because when we start cutting back on that wheel chamber pressure, we start to limit the steam flow coming through the machine, and that causes us to have a bottleneck on the compressor side of things. So then I'm going to go through a little bit about fouling. So as you can see there's a picture or a photograph of fouling and how it appears inside the turbine. And that basically is occurring when the steam goes from a dry condition to a wet condition. So from your superheated to saturated conditions, at that point is where you actually get the salts being slightly knocked out of the steam, and it builds up on these turbine blades as a result. So what fouling then does inside the machine is it increases the resistance, which will directly affect the wheel chamber pressure. It then also changes or modifies the blade profiles, which will decrease the isentropic efficiency, and a decrease in isentropic efficiency will result in slightly increased steam flow. I'll explain this a bit more in theory in a moment. Then we will also get, potentially with an increase in steam flow, we will see an increase in the outlet pressure. And with the increased wheel chamber pressure, we have a larger pressure over the whole machine, which will potentially result in a larger pressure force, and that needs to be absorbed by our thrust bearings. So going forward into a Mollier diagram, or an enthalpy-entropy diagram, here we can just see 2 cases of isentropic expansion, which is in the black arrow, and the real sort of expansion process in the red arrow. So what that is just showing you is that in a real steam expansion process, which is going from some superheated condition into a saturated condition, we get an increase in the entropy. And this is also then visually represented here as a slightly increased exhaust enthalpy. But as you can see, the extraction of energy is the difference between those two. So the more you increase your entropy, the less energy you're extracting from the steam, and so you would need more steam to have the same amount of work. This is a little bit easier to see sometimes on a temperature entropy diagram. And here we can actually, I've plotted 3 different cases. The one is the isentropic expansion, as you saw before, the real expansion to the same isobar, which is a constant pressure line, and then the real curve, but with an increased isobar as a result of the fouling condition. So here you can see that we've moved more to the right and even more entropy, but we've also climbed up onto a different isobar. And this is just exaggerated in this case for illustration purposes, but effectively that is the sort of transition that you have. And that is why, as a result of the fouling, you'll have, number one, an increased steam flow, but also these sort of changes that we see. So then going into the project itself, we had a budget of about 100 consulting hours for use with Optimum. And the aim of this project was to analyze the past performance and the maintenance of our maintenance interventions, here being the turbine washers, and predict the future on when these interventions are required, and to deliver a model that would be able to predict these interventions and then allow us to deploy that within our environment. So here I'm going to hand over to Boitumelo to go take you through the predictive maintenance workflow.
Thanks, Peter. So at this stage, we have a clear view of what the problem is and what we're trying to achieve. And so now we're going to move on to the solution we implemented. So the solution was comprised of various stages, which are shown in this workflow. And as I go through each stage in more detail, we will uncover the various challenges that we faced in building out the solution. The first stage entailed accessing and pre-processing the data, so essentially getting the data into a format that's suitable for building a predictive model. Once the data was clean, we performed some analysis on the data to extract features descriptive of turbine performance, and this, together with Peter's domain knowledge, enabled us to define the operating bounds of each turbine. Once we had characterized what healthy turbine behavior looks like, we moved on to building our model. And then finally, the deployment stage, which entails integrating the functionality into Sasol systems, so effectively making the technology accessible to the operators and decision makers, which Peter will cover in more detail later on in the presentation. Now we're going to look more closely at the data access and pre-processing stage. Sasol provided us with process data for 7 of their turbines. This was 6 years of data collected from 2012 to 2018 at 20-minute intervals. So this project was actually completed early in 2019, and so this is the most recent data that we had at the time. Initially, 4 variables of interest were identified, that being variables that could characterize turbine behavior, namely wheel chamber pressure, speed, steam throughput, and vacuum pressure. But through leveraging Peter's domain knowledge of turbine systems, we ended up ignoring the last variable, which is the vacuum pressure. And the reason for that is because vacuum pressure has a strong correlation to steam flow, which is one of the variables we're already looking at. And knowledge of this saved us a lot of time because it meant we didn't need to look at possibly applying dimensionality reduction techniques to the data. We were also made aware of the operating conditions of the turbine, where wheel chamber pressure has to be in the range 1,600 to 2,550 kilopascals, and speed has to be above 6,700 rotations per minute. So if we take a look at the graph on the right, which is a plot of the speed against time for a single turbine over that 6-year period, it means it's the operation in this region, which gives us information about the performance or the efficiency of the turbine. And remember, what we're trying to do is predict the remaining useful life of the turbine. In other words, when next will we need to maintain our turbine? And that deviation from normal operations can only be seen within this region. So for us to estimate the remaining useful life of the turbine, we needed to analyze the life cycle data of each turbine. And we can think of the life cycle as the period of time between two consecutive washes. But one of the challenges we faced is that there weren't any records or logs of when previous washes occurred over the 6 years. And so we had to work quite closely with Peter to see if it would be possible to tell when washing occurred based on the data. Because of this, we analyzed the low speed data, which is the data in the green region. Low speed data in general is representative of ramp up and ramp down time, overhauling, and washes. And we chose to look at the low speed data in isolation. So the scatter plot is only the data below the 6,700 RPM threshold. And we did this because we knew what we're looking for would be in that region. And by removing the high-speed data, it just meant we had less data to process, which saved us a lot of time. At this point, the aim was to look through the low-speed data and see if we could detect when washes occurred, so we can analyze the turbine life cycles more closely. After even more conversations with Peter, poor guy, he pointed out the turbine speed behavior when it's undergoing a wash. And in order to show that behavior visually, we plotted the scatter plot as a line graph. This red line represents a time when a wash occurred, and I'm simply going to zoom into the circled area to give a better view of the turbine behavior. So what Peter explained is that when you wash a turbine, the machine undergoes a series of ramp ups and ramp downs. You can see here it's turned off, then it's ramped up to run at about 800 RPM, then it's ramped down again. And this process takes about 8 to 12 hours. And this pattern is actually characteristic of washing a turbine, and it's something we never would have known without bothering Peter again. So we could find that working really closely with Peter, so coupling our modeling or data science experience with Peter's experience as the domain expert, worked really well in terms of influencing a lot of the design decisions that were made. From this, we were able to develop an algorithm to detect that pattern throughout the dataset. And this enabled us to have a log or record of when past washes occurred. Once we extracted those dates, we discarded the low-speed data, and this allowed us to focus more on the data that spoke to the operation of the turbine, so the high-speed data. At this stage, we have cleaned our data, and we know when previous washes occurred. So the next step is to analyze the turbine life cycles. To be able to visualize and understand how the behavior of a turbine changes as it nears the end of its life, we used our wash logs to effectively segment the data into a series of life cycles for that specific turbine. This graph shows the data collected within a single life cycle of a turbine. Earlier, I mentioned that we had 3 variables of interest for characterizing the turbine behavior, which was speed, wheel chamber pressure, and steam throughput. And we looked at various visualizations of the data, so 3D and 4D plots of different sensor combinations and ratios, trying to identify the key features, one of which was looking at speed against the wheel chamber pressure and how this varied over time, which is shown by this color bar. So the blue region would indicate the time right after a wash, and the yellow would indicate the time just before a wash needs to occur. And what we noticed was as we approached the next wash, so as the turbine gets more fouled, the wheel chamber pressure would rise and the speed would drop. And this is consistent with the theory. And this kind of plateauing behavior that we see in this region is the result of some of the control measures that Sasol has in place to prevent the pressure from rising past a certain point. Then we looked at the other life cycles of the same turbine. So for example, this turbine was washed 5 times within that 6-year period. And so 5 life cycles can be observed. And we use this view to see if the features mentioned previously, which were identified as being indicative of fouling, were in fact consistent across the other life cycles. Okay, so now we're taking a closer look at one life cycle and bringing in that third variable, the steam throughput. The reason for that is bringing in steam throughput provided another level of separation of the data points, particularly when looking at the color gradient, which speaks to the period of time between 2 washes. In this view, what we see is that the steam throughput is rising. And from a practical point of view, the reason this happens is because as salts continue to accumulate on the blades of the turbine, more and more steam is required to maintain the same throughput. But eventually, a point is reached where the expected throughput can no longer be maintained. So that throughput gets pulled down by the pressure limit, which is limiting the steam throughput. And it is at this point where we know our system is operating inefficiently. From this, we could determine what the operating threshold needed to be, which is this red star. So this is where we don't want to be operating, or anywhere too close to this region. And we can see that that point corresponds with the wheel chamber pressure threshold, which is chosen by the operator, and the point where we start seeing the decrease in speed. So once we are within certain bounds of the operating threshold, this is when we typically want to wash the turbines, so we can start operating in the blue region again. So just to recap, at this stage, we have identified our operating threshold, in other words, the point we don't want to reach. But we know that as time progresses, so as the turbine reaches the end of its life cycle, we get closer and closer to that threshold. Meaning that the 3D distance between the data points and the threshold over time will decrease. So we started by calculating the distance between each data point and the threshold. And that distance between the data points and the threshold is what this graph represents, where the y-axis is the log of the distance, the x-axis is time, and the color bar in this instance represents the wheel chamber pressure. Each graph here is a separate life cycle, and we can see that in general, each graph very gradually tends to 0 over time. Because remember, the x-axis essentially represents that operating threshold which we are approaching. The final step required fitting a linear function to the distance data. In this process, we made use of a moving window, where the window size is a certain period of time which gets determined by the operator. And as the window moves across the data, at each step, a linear function is fitted to the data. You then get this collection of linear models. And the reason we used a moving window was to ensure that the model adjusts its predictions according to the latest information. And you can see how the model keeps adjusting itself by looking at these decreasing gradients as we move through time. And this is exactly what we expected to see. We then get an average of the models to get the general trend of the overall data. Then finally, we extrapolate that average model to the x-intercept, in other words, to the operating threshold, which then tells us what the remaining useful life of the turbine is. At this stage, we are very happy because we now have a predictive model that we can verify. So we verified the performance of the model by applying it to historic unseen data. And these red lines you see here serve as the markers of what the model predicted the next wash will need to be. So if we look at the first graph, we can see that the turbine was washed around August, September. But according to the model's prediction, the washing could have happened a few months later. But from the gap in the data, which is about a month long, we know that the turbine was actually overhauled, which explains why it appears to have been washed too early. We also see that shortly after the overhauling, the efficiency of the turbine dropped quite rapidly. And in this instance, Peter and the team knew it was due to the poor steam quality at that time. So really the results of the model are meant to serve as supporting material for the operators and the decision makers. And this is important because the intention of the predictive model was not for it to be used in isolation or independent of the operator, but to serve as an additional tool or assistive technology for defining a more holistic wash schedule. For the second life cycle, a wash was performed around September, but the wheel chamber pressure was still quite low. You can see that we're still in the blue-green region. So we washed it too early, and we can see that the prediction had it at a few months later. And not only that, we noticed that shortly after the wash in September, which marks the beginning of the third life cycle, we could already see the wheel chamber pressure starting to rise again. We're already moving into that yellow region. And this just highlighted that the quality of the wash was not so great. So from an operational point of view, this allows operators to not only predict the future, but also have a retrospective view of why certain decisions were made and how they can be avoided in the future. Once the model was built, the next step was looking at how will this technology be made accessible to the relevant people within Sasol. And Peter will give more information around that.
Thanks, Bottleneck. So now we've got a model that has been built. It's now in our hands. Now we need to, from the Sasol side of things, integrate it into our workflows and our operational environment. That had to factor in a few different things. The one is, how are we going to actually interface with this model and this app? And then how does that integrate itself into our operational databases and things like that, so the back-end side. And then I want to just touch on some of my my learnings in that, because I think the audience might find some use in that information. So on the right-hand side here, you can actually see an example of what the GUI interface looked like. On the left-hand side, we've got a summary section where it would just cover the operation of each machine since the last wash. So you can see there's breaks in operation, but it was never washed in that particular period. And yeah, this is essentially just a high-level look at each machine, and then you can deep dive into a specific unit, so in this case unit 7, and look at what that information looked like for the last wash or the last number of washes in the time frame that you've requested. So here you can actually have that retrospective look to see, did we actually improve? Are we moving further away from that high wheel chamber pressure, getting these nice dark blues and things like that? So that retrospective analysis is done visually, and just as a secondary point to the actual washing procedure itself. So then other interface considerations. So on our GUI interface, essentially for people like planners and maintenance managers and things like that, they're not necessarily looking to dive into the details. They want to know the information off the bat, nice and quickly, in a summarized and concise form. So here we can see that landing page of the app. You essentially select our historian data, you import it, you run the model, and then it'll provide you with a table. And here you can actually just vet, are there some cases where these machines might want to or need to come off at very close intervals to one another? And then you can actually shift around those schedules, maybe wash one a little bit earlier based on production availability and things like that. So it allows you to plan that and to just have that sort of visual way, or tabulated data to make that decision. Something to note as well on your web apps is that typically it'll just log the next action that should be done. So if you click the 2 buttons in quick succession, then it will pull the data, but then the next coding window, it'll actually run the second one, which may not be when you've actually gotten the IO back. So in cases like this, it's good to use something like a processing dialog to prevent the user from adding any more inputs to the app. Then in terms of the deployments on the back end, we have quite a interesting situation where we have two different types of historians, actually essentially backups of one another. One is a Honeywell historian and the other one is a OSIsoft Pi historian. Both of those historian instances also have OPC server deployments on top. So we had a luxury in terms of how we could integrate this app into our operational facility. And I started off with using the OPC toolbox, which allowed me some sort of graphical way of exploring the server, seeing how I'm going to get the data, and then you can also create functions to go and pull certain functions or pull data or utilize any OPC functions. And that just helps with creating code if you don't specifically know the architecture. And then the other methods is actually using either the DLLs or the APIs natively within MATLAB, which you could do via the .NET add assembly or a load library call. And this actually is a slightly better method because the APIs carry a little bit less overhead and they remove some of the inherent limitations that might exist on the OPC deployments. And then the last one was I was struggling to get the Honeywell API natively into MATLAB, but I was able to actually pull that into Python. And because of some other work that we're doing using coolprop within Python, we actually decided to just use Python as a basis for that. So as we made that decision, that then requires us to just ensure that we have correct MATLAB wrappers to essentially take whatever is in the Python or .NET scripts and make sure that it's compatible with the data coming into MATLAB. And then the last step is once you've got all that data, you process it and you figure out some of the sort of downsides maybe of the GUI, and you optimize that to make sure it's quite user-friendly. And in that instance, we found that the information was taking quite a while to process. And as Boitumelo mentioned, there's multiple linear models that is being done because you've got that moving window. And essentially that takes quite a lot of computation. And what we're doing here is actually then just making sure that we can leverage our multiple CPUs on the machine by using a parallel for loop. But that in itself mandated that it was a little bit of a rewrite in the code, just in terms of how the function sort of communicates to the for loop, because you still need to keep track of which machine you're dealing with. And that you can do quite easily. You can look in the documentation of MATLAB, but you essentially would use a data queue to make sure that you can get the values back. Last thing is that when you use something like a parallel for loop, it's going to start a parallel pool with however many workers you've got set, and that takes some overhead. So these are not necessarily advised for situations where the overhead is more than the cost of the processing. Then some of the interesting points on the historians that I'd like to mention is essentially they look very similar in how you would call and get data from the historians. You've got these tag constructs and you've got functions that are built onto the tag. But what's interesting here is I've got a tag construct and I then have a server construct, and the fetch data request is then on the server construct of the Honeywell side of things. Whereas if you look at the Pi side, you've got the same tag construct, but then the tag construct has something called a summaries or a way to fetch data based on some sort of calculation or something like that. You don't have to put in a calculation. You could just ask for the raw data or something like that. And then here's an example of, say, the current value. So the important thing here is that each point actually sends a request and not necessarily each server. And that is just the difference in how those connections are handled. So on the Honeywell side of things, the connection is handled as a per server request, and the timestamps and the requested date is aggregated in that sort of server instance, and you don't need to make sure that it's there in each call. And whereas on the Pi side, it's actually handled as part of these functions. So that's handled internally within that summaries function or method, for example. Something to note is that because of this, the way that this occurs, when you want to run through multiple tags serially, it's actually slightly faster to use what OSI has built into their API, and that's a point list. So that's essentially a similar way of doing it to the server, in that you've got a list of points that you want to then request the exact same data for. So that makes things a lot faster because you can actually parallelize the call on the server side, and you don't have these multiple IO waits that you do when you serially request the data. So please feel free to visit the support documentation. I only have the OSI support website documented here. If you have a Honeywell server, you should be able to get hold of the documentation for that in PDF form. And going on to actually getting, so now we've got this function in MATLAB and in Python, but we have still an issue that whatever these APIs are using, they're actually .NET APIs. So they're using system type variables. And firstly, you need to get, because you're using Python for this, you need to get them into Python data types, but preferentially you would choose data types that are sort of analogous to the MATLAB data types. So in this case, things like doubles, integers, singles, those are very easy to move between Python and MATLAB. So that is fairly trivial. But moving them from a system data type to a Python data type might not be. So there's various ways to skin this proverbial cat, and that is, one of them is to use like for loops or looping through the arrays or the constructs, and actually then converting each sort of cell or actual data point individually. These are typically quite time consuming, especially when you compare it to the next comment, which is actually a GitHub post. I've put it in there for interest, and you're welcome to go and view it. This essentially is a memory move of certain data types that are identical to Python data types, and that makes it very quick to convert these data types to a Python data type. In our case, all of the data was actually doubles, and most process historians store values in either doubles or integers, or maybe booleans. I've come across very few that are actually using string data types. So yeah, that actually works for most or all of the data that I was dealing with. The last thing that's a bit tricky is the date time. So that was coming through as a system date time, which you could either store as a string value, but then passing the string and making sure that your date is the same on either end is quite time consuming. Passing strings is obviously not just a single action per data point. You've got however many characters you have in there. So obviously passing a character string is quite time consuming because you have multiple characters that you need to pass. The other option, though, is when we make this call to the database, we can actually request the date time as a UTC date number, which means that it's very quick to essentially change that over to a date time in MATLAB. It's essentially just an addition to the 0 date number and getting that back, and that is just essentially a float 64 or a double data point. So that it makes that conversion quite easy. And I would advise, if you're going to do something like this, to use that sort of method, rather convert it into a known date number and then use that formula going forward. And then lastly, now we've got this model, we've actually been able to deploy it, and now we can use it. So essentially we managed to create a model within the 100 hours of available time. It provides us with retrospective analysis, it's repeatable and comparable, and it does exactly what we needed to do. And that is, in the case of efficiencies, we weren't specifically requiring that we look at the efficiency necessarily of the turbine, but we were looking more for the point of operation where we start to bottleneck the facility, because that is a much bigger loss for us, and that was our main goal. And so we've now got this model, we've integrated it, and we've used it. So lastly, in terms of a workflow like this, is just some details that is handy to remember. That is, if you can understand your problem from a first principles or physics or some sort of design basis, then I would urge you to do that, because it might highlight points where you can actually take a physical and an analytical approach to either minimize the dimensionality of the data or understand relationships between certain data points so as not to duplicate a relationship. And then also understanding your deployment requirements. So in our case, we wanted it to be a GUI type deployment so that we could have the retrospective analysis. You could also, if you have a specific goal, write this into a script that runs in the background, and then just to deliver, say, a report or a single value or whatever the case might be in the back end. But like I mentioned, we wanted the retrospective side of things. And then also understanding leveraging of the sort of expertise that's available to you. So in our case, I'm not a data scientist by trade, and so the data science portion of it would have taken me much longer to do and implement, and my expertise lies on the machines and how I can bring some knowledge into the model based on that. So it's important to collaborate in things like this, and that this whole process, as we've detailed, was a massive collaboration between the two parties, making sure that my goals as a technical person were achieved, and also bringing that technical knowledge into the data science, and Optimum or Boitmiller being able to provide some visual sort of evaluations and things to essentially see, is this model doing the right thing? And that was a really good way to work, just leveraging those two things. So I would advise that as well to whoever wants to approach a problem like this. And then for client personnel that are working and breathing into these operational environments, just establish whether you have any of these problems and whether you can find a better or more efficient way of dealing with information that you deal with on a repeated and frequent basis. Question that and see whether you can improve and expand on what you're doing, moving stuff away from a manual action into something that is a little bit more automated, that gives you a bit more time to do sort of these interesting examples and workflows and sort of optimize your time a bit better. But in order to do that, you need to get to know your systems, understand what the limitations are in terms of data flow and what data is available and those kind of things, and what you could actually achieve. And to do that, you might also identify some future hurdles and projects that might need to be done in order to make this a reality. So yes, thank you for your time. I hope you guys enjoyed it. And I hope you found value in it. We'll now take some time to answer some of your questions. Also feel free to contact us if you have any specific questions around the content.
Thank you, everybody.